Life requires energy. The universal biological fuel is a molecule called ATP, or adenosine triphosphate. ATP stores chemical energy in the form of a high-energy phosphate bond. As the name suggests, it consists of an adenosine ring with a chain of 3 phosphate groups attached. The last of these phosphates can be split off to release the energy within the bond, resulting in adenosine diphosphate and free inorganic phosphate. This energy is needed to keep cells alive and is used from processes from muscle contraction to producing the thoughts your brain is having right now. The hydrolysis of ATP can be reversed by the addition of inorganic phosphate to ADP. However, this of course requires energy and is performed by a molecular power generator called ATP synthase. Here we see an atomic model of F1-FO ATP synthase sitting in a membrane. This molecular motor is found in the mitochondria of eukaryotic cells and is responsible for making most of the ATP. Mitochondria, the powerhouses of the cells, turn over around 60 kilograms of ATP every day in an adult person. A long chain of biochemical processes convert the energy stored in food into a proton gradient across the inner mitochondrial membrane. These protons drive a rotation of the turbine within ATP synthase, resulting in the synthesis of ATP. Like all generators, ATP synthase consists of 2 separate motors coupled together. Within the membrane, we have the FO motor, named after the binding of antibiotic oligomycin, and at the top we have the F1 motor from factor 1. The FO motor is a proton-powered motor. It is thought that protons flow through a channel open to just the intermembrane space, where they bind to a ring of protein subunits, rotate 360 degrees, and exit through another channel exposed only to the matrix. The net flow of protons driven by the proton motor force provides the energy for the generation of rotation. The torque generated in the FO motor is transferred to the F1 motor by a central stalk or shaft. The F1 motor is responsible for generating the ATP by addition of phosphate to ADP. The top of the central stalk acts similarly to a camshaft, so that as it rotates within the F1 motor, it causes conformational changes of the catalytic subunits. The catalytic unit is made of a dimer of subunits, and there are 3 of these arranged in a ring. Catalysis occurs at the interface between the dimers. If we concentrate on one dimer, we can observe 3 distinct states. First, ADP and phosphate bind to the catalytic site. The central shaft then rotates 120 degrees to rearrange the molecules. Next, the enzyme undergoes a further 120 degree rotation, and the ADP and phosphate are fused together to create ATP. The enzyme then rotates again to return to the starting position, where ADP is released and ADP and phosphate can be bound for the next cycle of catalysis. One key aspect of this relationship is that catalytic subunits must remain stationary with respect to a rotating central shaft. This task is performed by a scaffold on the outside of the complex, referred to as the peripheral stalk. Recent work has shown that what was once thought of as a rigid scaffold is actually dynamic and is able to accommodate the changes necessary for most efficient function. Looking at this machine in its natural environment by electron chromatography of intact mitochondria has shown that ATP synthase dimerizes to shape the mitochondrial inner membrane into their signature cristae shape. This turbocharges ATP synthesis by focusing the proton gradient near ATP synthase.